All right. So today our speaker is Leonardo Maltoni, and he has worked with 10 years ago. He has graduated this year. So he will be giving talk on towards Bernstein's presentation of the affine Hecke.
Okay, thank you very much for the opportunity to speak here and for the invitation. So I hope you can hear me well. Look, so I can hear you well only if you speak near the microphone, I think. Otherwise, it's a bit a problem. So if I don't hear a question, like you can scream it or, or come towards the microphone. So I will talk to you about some first steps, actually, towards a Bernstein presentation of the affine Hecke category. And so what is the idea? We will start with a Coxeter system, WS, and we associate to it a Hecke algebra. Then some problem. Then to this we associate some more structural object, which is the Hecke category, and we will be interested in this when our Coxeter system is the affine Weyl group, and so we call the affine Hecke algebra and the affine Hecke category. So the affine Hecke algebra contains a lattice which lifts the coroot lattice of the affine Weyl group. And this lattice has a lift in the category of the affine Hecke category, which is called like Wakimoto sheaves. These are objects that correspond to this little theta lambda and are called Wakimoto sheaves. So we will introduce these objects and try to study them. The idea is that the subalgebra generated by the theta lambda is very interesting and gives many properties of the affine Hecke algebra, and so we want to study, like we want to upgrade this to a categorical level. So some background. Okay. On the Hecke algebra. So as I said, we start with a Coxeter system. And we associate to it its braid group. So it's the same amount, same generators, but we get rid of the involution relation and only consider the braid relations. So for example, the permutation group and its associated braid group, which is the standard braid group on n strands. And so we can construct the Hecke algebra from this data, which is a ZVV inverse algebra generated by elements delta S, one for each S in S, under the following relation. Sorry. And then we have the braid relation. So we have this deformed version of the involution relation and then the braid relation. So in particular, this is a quotient of the ZVV inverse algebra, group algebra of the braid group. Now consider a reduced expression for an element W in W, which means the composition in the generators, which is minimal in length. We can lift this to the braid group, and this element is called, in the braid group, is called, so with the corresponding generators, is called a positive lift. And so also to the Hecke algebra. And we have elements delta W equals delta S1, delta Sk. These are well defined, and also by the first relation, by the involution relation, they are invertible. Okay, so now I want to change page. Okay, that's a bit, okay. And like, to give a motivation to this definition, let me make this remark, and also a geometric interpretation of this Hecke algebra. Let us consider the following setting. So if G is a reductive group containing a Borel B and a maximal torus T with a structure over FQ, which is split, we can consider the algebra of C-valued functions on the FQ points, which are B invariant for the action of the Borel, of the FQ point of the Borel. And we take this ring with convolution. Then this is isomorphic to the Hecke algebra associated with the Weyl group, which I denote WF for the finite Weyl group, specialized to C, specialized to this C algebra via the evaluation sending V to Q to the -1/2. So the study of representations of the Hecke algebra is important for the study of representations of finite reductive groups. And we also have an affine version. So here we have to consider algebra of function over C double parenthesis T, which are Iowa-Hoare invariant on both sides under convolution. And this is isomorphic to the affine Hecke algebra with the same specialization, where the affine Hecke algebra is associated to the affine Weyl group. And what is this? This is the finite Weyl group semi-direct product with the coroot lattice, which is contained in the co-character lattice. So it has an action of the Weyl group, so we can take this semi-direct product, and it is also a Coxeter system if we add some affine reflections. And then we have a Coxeter system which to which we can associate a Hecke algebra. And so we have a similar interpretation of the Hecke algebra. So what do we mean by categorification of this? So we want to build a category, which will denote H, such that its Grothendieck group is the Hecke algebra. So we want a category which is either abelian or additive, or something for which the Grothendieck group makes sense. So we will take an additive category. We want it to be monoidal because we want that the Grothendieck group has the structure of a ring. And also we want it to be graded because we want a ZVV inverse action, and this will correspond to the shift. So there are several incarnations of this Hecke algebra, Hecke category, and we need some additional data. So let us consider K to be a commutative ring. and H to be a realization. Sorry. Of W. What does that mean? It means a free finite rank K module with a W action, like which is a representation of W, such that it contains some elements called simple coroots, and its dual contains elements called simple roots, mimicking what happens in the usual root system. So an example of this is actually the co-character lattice tensored with K for the case of a Weyl group. And roots and coroots correspond to the usual roots and coroots in that case. Now, from this data, so we also call R the symmetric algebra over H dual. And from this data, we construct a category. So the first incarnation that we will see is the algebraic Hecke category. And this is a subcategory of the category of graded bimodule over R, generated by some object Bs by tensor product, direct sum, shift in the grading, and direct summand. So what are these BS's? BS is for each simple reflection, the tensor product of R with itself over the ring of invariant for S, shifted by 1. And if we take all products of these and then note sums or shifts and those summands, this gives a category called, whose objects are called Sorgel bimodules. Introduced by Sorgel, of course, and it has like a recent variant by Abe, which is better behaved in some cases, which I will tell you. So this is the algebraic version. Then we have a geometric version, which is only available in the Weyl case, so not for any Coxeter group, which this time is a subcategory of the equivariant derived category of the sheaves of the flag variety with coefficients in K, generated by the constant sheaves over the minimal Schubert varieties, which are not trivial, shifted by 1 by the same operation. So tensor product, direct sums, shifts in the cohomological degree in this case, and direct summand. And also we have a affine version if we take the affine flag variety. So G double parenthesis T over the Awahori. With coefficients in K. And so this is also a construction due to Sorgel partially. But what we obtain in general, like in any characteristic, are what are called parity sheaves. So, and this is a construction by Juto, Mautner, and Williamson. So if we take the standard realization for the Weyl group, then we have a functor from the geometric category to the algebraic one given by equivariant cohomology. And this functor is an equivalence under some conditions. So it depends if we take the original version of Sorgel bimodules, then we have to ask for the realization to be reflection faithful, which usually fails in positive characteristic, but with the ABE version, it works. And then we can consider a third categorification, which is the diagrammatic category. And this is a presentation by generators and relations of both categories, actually. So it was present like of both category when they are well defined. So in general of the both Sorgel bimodules, and when they are defined, so in the Weyl case, also for the geometric category. And this was a result by Risch and Williamson. So I didn't say that the category was introduced by Elias and Williamson. So to give a reason why this is called the Hecke category, let me state the theorem which in some sense motivates this construction. So it can be proved in either of these settings, and it's a categorification result. So we have to suppose that K is a complete local ring. And then we have that the Hecke category in either of the versions is Kroll-Schmidt. And that it's split Grothendieck group, which is a ZVV inverse algebra, because it's a monoidal graded category. It's isomorphic to the Hecke algebra. And the object BS, so in the case of geometry, these are the constant sheaves shifted by 1 over PS over B, correspond to the element B, little bs in the Hecke algebra, defined as delta S plus V. Third, we have a classification of the indecomposable objects up to isomorphism and shift. These are parameterized by the element of W, so the Weyl group or the Coxeter group in general, and we call BW the element corresponding to W. And so this gives an interesting basis over ZVV inverse of the Hecke algebra, which is not the standard basis, but it's a canonical basis in some sense. It's called a p-canonical basis. So it's very useful for character formulas, as shown in a paper by Risch and Williamson, and Achar, Makizumi, Risch, and Williamson. And it's a good replacement in some sense for the Kajan-Lustig basis for positive characteristic. And for p equals 0, it is actually the Kajan-Lustig basis. Okay, so this justifies the name of Hecke category. And now what we want to do is, I think first, let us give more detail for the diagrammatic category, which is the one I used more. And then we will come back to our problem. So one can notice that the Hecke category in both the geometric and the algebraic version is generated by some subcategory, which is called the Bott-Samuelson subcategory, by direct sum, shift, and direct summons. And of course, this Bott-Samuelson subcategory is just the category generated by the BS by tensor product, because it's the only operation which is missing. And then the other steps are just formal. because we can add formally direct sums, shifts, and take the Karubi envelope. Why it is called both Samuelson subcategory, because in the geometric setting, this corresponds to the direct images of constant sheaves via the Bot-Samuelson resolutions of the Schubert varieties. So for those who know a little bit of that stuff, this is why it's called like that. Now, so the idea is that we want to present, so to give a presentation of this subcategory. And this is done really explicitly via diagrams. So we introduce objects as tensor product of BS's, which are just formal generators for each S in S, and we represent them as sequences of colored points. Like for example, if red is S1, yellow is O. Yellow is S2 and green is S3, then this colored sequence is BS1, BS2, BS3. And then morphisms are k-linear combinations of decorated circle graphs. So we have two objects. We represent the source on bottom and the target on top. And we allow, so we want to construct a graph connecting these two sequences of points, so a colored graph, where we allow some kind of vertices. So the generating vertices are dots and trivalent vertices for each color. And then we have a two-color vertex of this form, which is a two M-valent vertex if S and T, so if ST has order M, less than infinity. And so, for example, here is a circle graph. So here we have, so for example, this, we have some dots, which are the one valent vertex. We have a red trivalent vertex on bottom, and then we have a four valent vertex, which means that the reflection associated with red and the one associated with green actually commute. So ST equals TS. We have just M equal 2 in this case. And we can construct more complicated diagrams. Also, we can decorate them by polynomials floating in the regions, so in the connected components of the complement, and this gives a graph. So we identified this graph. So we identified up to isotopy, and some relations, which are like quite a lot, and I will not detail them, but they allow to construct explicitly this category. And the benefit of this version is that you can explicitly compute morphisms. So let us give just a little example. So one of the most simple, like simplest morphism that you can construct is from BS to the unit, given by a dot like this. So this is a well-defined morphism in the diagrammatic category, and it corresponds, for example, to these morphisms in terms of circle bimodules. From BS, the object BS, which is, I recall this product, to the unit, which is R, and this is just multiplication. You take the element in R and the element in R and multiply them to obtain an element in R. And this is what corresponds to the dot in the terms of circle bimodules. And geometrically, here you have the constant sheaf on PS mod B shifted by 1. And you go towards the skyscraper over B mod B. And this is just the morphism associated to the unit, to this unit, adjunction unit, where I is the inclusion of B mod B inside PS mod B. So we can like pass from one version to the other via functors, which are, so I mean, the third one is defined only if we are in the geometric setting, so in the Weyl setting. But you can translate diagrams into morphisms in terms of circle bimodules or sheaves. And then like the morphism which I drew just some minutes ago would be a very complicated morphisms in terms of circle bimodules. And this is the advantage of this diagrammatic presentation. Okay, so let us go back to our problem. So consider the affine case. So I mentioned that the affine Hecke algebra contains elements theta lambda, which lift the coroot lattice. What does that mean? So if I take lambda to be a coroot, and I decompose it as mu minus nu, where mu and nu are dominant, then I can define theta lambda to be delta mu times delta nu inverse, where delta nu and mu are the standard basis element associated with mu and nu, which are elements of the Weyl group. And then one can show that this theta lambda has the property that theta lambda times theta lambda prime equals theta lambda plus lambda prime. So they form a commutative subalgebra of the Hecke algebra, which is extremely interesting and useful to study the representation theory of the Hecke algebra. Namely, they determine this subalgebra contains the center. And the properties of these subalgebra are encoded in what is called the Bernstein presentation. Of the affine Hecke algebra. So our goal is to categorify these objects. So the question is how we categorify the theta lambdas, and more generally, the delta W. And then how do we study the category that correspond to this subalgebra? So to do so, we consider not only the Hecke algebra, but the Hecke category, but the homotopy category of the Hecke category. And inside this, we can consider these two complexes, big delta S and big nabla S, which I can describe there's a shift here and a shift of -1 here. And diagrammatically, this is like a lower dot, so the morphism of above, and an upper dot, which is like the dual of the morphism of above. And geometrically, these corresponds to the distinguished triangle of standard IC and skyscraper IC and co-standard. So they can be seen as resolution via ICs of the standard and co-standard sheaves. And actually this homotopy category of the Hecke category, which can be seen as a triangulated version of the Hecke category, it was considered by Achar and Risch as a modular version of the mixed equivariant derived category. And so actually these objects correspond to mixed perverse sheaves, but I will not detail this. And so we can consider delta W as product of standards and nabla W as product of nablas, where S1 SK is a reduced expression for W. And in the affine case, we can consider big theta lambda to be big delta mu times big nabla nu. And this is the Wakimoto sheaves, which I mentioned. Which categorifies, so I didn't explicit that the big delta W categorifies the little delta W, because delta S categorifies the delta S. You can see this by taking the Grothendieck group of the triangulated Grothendieck group of KBH, and then you get that the class of delta S correspond to BS minus V, which is exactly delta S, and nabla S correspond to delta S inverse. And so delta W correspond to little delta W, and big theta lambda correspond to little theta lambda. So these objects actually categorifies in this triangulated version of the Hecke category our lattice inside the Hecke algebra. So the goal is to study morphism, like the first information that we can ask for in this subcategory is morphisms between these objects with some shifts. So how do we attack this problem? So actually the same category was considered by Rouquier as a categorification of the braid group. So what does that mean? He considered Fs, so he called Fs what we called delta S, and Fs inverse what we call nabla S. And this is, so I will keep this notation because it actually it makes a difference if we consider them inside some different categories. So what Rouquier considered was the category generated by all products, I mean, by all these Fs and Fs inverse by tensor products. So all possible products of these standard and co-standard complexes. And all these products are called Rouquier complexes in his honor, inside the category of the homotopy category of the Hecke category. And he showed that Fs inverse is just identity, and Fs inverse Fs also, and that they satisfy the braid relations. So actually isomorphism classes of Rouquier complexes are at least a quotient of the braid group, and it is conjectured but that they are actually the braid group. It is proved in finite type by Brav, Thomas, Kovanov, Seidel, and Jensen, and it is a conjecture for all other types. But at least they form a quotient of the braid group. So this is why sometimes this is called the two braid groups, like a categorical version of the braid group. It was introduced to study actions of the braid group over categories. But for us, what is important is that our Wakimoto sheaves are examples of Rouquier complexes because they are a product of delta and nablas. So to study morphisms between Wakimoto sheaves, we study morphisms between Rouquier complexes. And the first thing to do, because we want morphisms in the homotopy category, is to find good representatives. So Rouquier complexes sometimes admits what are called minimal subcomplexes. So subcomplexes which do not admit contractible summands and which are in some sense, like in this sense, they are minimal, and so they are the best choice to study morphisms between them. This is not always available, so we have to assume that the category is Schmidt. And even in this case, it's very hard to find minimal complexes. But in the case of characteristic 0 and type A1 affine, we know the minimal complexes and can use them to compute morphisms between the corresponding Wakimoto sheaves. In general, this is not so easy. Now I will pass to some slides that I have. So let me, okay. Okay, so can you see? Yes. No. Yes. So in general, if we are not in this, like if we are over Z, for example, and we cannot assume that the category is Schmidt, then the notion of minimal complex can even not make sense. But also, if it makes sense, as I said, it's very hard to find minimal complexes in general. So a naive representative for Rouquier complex is like just the product of the complexes in the category of complexes. So you have seen that the standard and co-standard are concentrated in 2 degrees, like 0 and 1 and 0 or -1. So products of this complex gives gigantic cubes. Like if you take n of this, then you have 2 to the n possible products. And this, for example, is a picture of the complex Fs, Fs, Ft, Ft, Fs, Fs. And this is a representative, but we can do something better. So we can simplify this by finding inside it some distinguished subcomplexes. So for each subword of SS, TT, SS in this case, there is a subcomplex which contracts to a single object. And this contraction is done via an homological algebra technique, which is called Gaussian elimination for complexes. And actually, it amounts to say that the cube is a contractible CW complex for the case of STS. If we take another subword, for example, SS, then it corresponds to another subcomplex, which is associated to another CW complex, which in this case is this blue square with 2 triangles. And the contractibility of this CW complex amounts to saying that this subcomplex of the Rouquier complex, sorry for all these complexes, is can be contracted to a single object. And we can do this for all subwords. And actually we obtain a representative which is much simpler, in which the vertices are not all possible sub-expressions of SS, TT, SS, as in the beginning, but only subwords. And this is like what the complex looks like. And we can describe morphisms explicitly. And this is like very useful to compute morphisms between Rouquier complexes and then Wakimoto sheaves. So as I said, in characteristic 0, we also know the minimal complex of Wakimoto sheaves. And then we can use this to compute cohomology. I mean, to compute morphisms between them. And this is a table representing morphisms between Wakimoto sheaves in type A1 affine. So you can see the rows correspond to different values of n, because the coroot are just the integers in this case. And we can reduce to the case of a negative, like theta of a negative integer towards the unit, thanks to the properties of Wakimoto sheaves and Rouquier complexes. And each column corresponds to a cohomological shift. So this is the case of in which we know minimal complexes. But in the general case, it is much more hard to compute minimal complexes, and in some cases they are even not well defined. And we can simplify the objects in the first place, and then simplify the DG module of morphisms, which I did not introduce, but you can, once you have chosen representative for these Wakimoto sheaves or these Rouquier complexes in general, the morphisms between them in the homotopy category can be seen as the cohomology of the DG module of morphisms. And what we have in general for A1 affine is a model for this DG module, which is simpler than just the naive one. But if we specialize to the antispherical Hecke category, which is a quotient of the Hecke category by some corresponding to to the parabolic subgroup corresponding to the finite Weyl group, then we can actually compute morphisms between Wakimoto sheaves, and what we obtain, let me show you. So where is this? Okay, I will find the file. Okay, I will show you by my other screen. I don't know why it's not in the tablet, but I can show you from here. Can you allow me to share the screen also in the? I can still not share the screen.
Let me just
Okay, now I can. Okay. So can you see my screen?
Yes.
Okay. Okay, so this is what I wanted to show you. This is the table of the cohomology, of the morphisms in the homotopy category between Wakimoto sheaves in the antispherical Hecke category in type A1 affine. So what you see is like this case in the stairs, in the diagonal stair, are the only known torsion entries. Everything which is on bottom of that is torsion. So you can see that the pattern, like we can describe the pattern, even if it's not very clear from this picture, but like we have a description of the pattern in this case, but it shows you that like morphisms, even in the quotients, are very complicated in general, like for general coefficients. And so like this subcategory of Wakimoto sheaves already in type A1 affine is extremely complicated. And of course, and in particular in positive characteristic, like the behavior here is very interesting to study. Like for example, each cell, how do you read this tableau? So this table, sorry, each cell represents, like, let's take k equals z for the moment. So 5, 3, 2 in column represent z over 5 plus z over 3 plus z over 2. So this is the torsion that we have in degree. So for n equal 12 in degree 16, and so on and so on. Like in general, actually this table works for any Cartan matrix of type A1 affine, and the numbers correspond to cyclotomic polynomial, like 2-color cyclotomic polynomials, for those who knows this. But like already for Z and for just integers, this is already an interesting behavior that deserves some further study. And I think I will stop here. Sorry, I cannot hear you.
Can you go back to the slides before?
Oh, yes, yes. So let me, I can show you them from here. Okay. So which one?
One back. Oh, keep going back.
These are all the slides. I don't know what.
All right, well, anyway, let me start something else. So you mentioned this connection economic basis.
So I'm sorry, but I can hear you only very badly. So maybe.
Yeah, maybe here and share this slide.
Hello, can you hear me now?
Yes, a little bit better.
Yeah, so you mentioned this connection with the p-canonical basis.
Yes.
And so from p-canonical basis, you can construct p-paternalistic polynomials. That's right. And so my question is, does any of this technology help in computing p-paternalistic polynomials?
Yes. So like the diagrammatic category is actually very useful to compute p-canonical basis, because it gives like explicit way to compute morphisms in the Hecke category. And then like you can like it's in this way that you can construct algorithm to compute the p-canonical basis, but still it remains very hard to compute it. I mean, I can give you some more detail. Like you can reduce the computation of p-canonical basis to some intersection forms, let's say. And this is already makes sense in the geometric setting, and also in the bimodule setting. But with the canonical basis, you can reduce this computation of intersection forms to computation with the diagrams. So it's still much more complicated than in the case of the usual Kazan-Lustig basis, because in that case, there is just an algorithm for the algebra, but you can give an algorithm with diagrams. And this is how what we know about the p-canonical basis actually is very, I mean, not only, but it uses a lot this diagrammatic description.
So my second question is, can you apply some of what you're saying to compute characters of tilting models?
Sorry, can you say it again?
So can you use what you're saying to give actual, characters for tilting models? Maybe not everything, but a certain classes of tilting models.
So, I mean, there is a character, I mean, you mean like there is a character formula for tilting modules depending on the p-canonical basis?
That's correct.
Yes. And then
Yes.
if you compute the canonical basis, then you have this formula for tilting modules. So your question is?
Yeah, so can you actually compute characters in some tilting models with just actual examples?
Oh, so like I don't have an example here, but yeah, so you can compute those characters.
Okay. Well, I mean, in principle, but I mean, can you actually do it that?
Yeah. Like, but the canonical basis is known, for example, for A1 affine is completely known. or like in some types it is completely known, and then also the characters of the tiltings are known. But
Well,
like,
maybe for like type G2, for example, the rank 2 cases.
sorry, type what?
Just for like the rank 2 cases. Can you do some of the rank 2 cases?
I didn't hear you, sorry.
Oh, sorry, the rank 2 cases, like B2 and G2 and A2.
I think it's known also in those cases, but I'm not sure. Like in rank 2, it should be okay. Like it should be known.
Because we actually have to promote for G2. But we were not successful getting any information for G2. So for characters and tilting model for G2.
So I'm not sure, but it should be known. Like there's a paper by Jensen and Williamson in which they give computation for the canonical basis, and I think there's also G2 there.
Okay. Thank you. I'll take a look.
Okay. Sorry, I don't know exactly, but I think that that's known.
Okay, thank you very much for your time.
Okay, any other question? So how did you do the computation? Like, did you do by hand or like programming for your full complex?
I'm sorry, if that was a question, I didn't hear you.
I'm just asking, like, how did you do the computation for the
Can you say it again?
yeah, how did you do the computation? Like, did you do it
Ah,
by hand
so
or
which computation? This one or the last one?
for the last one and the complex, the complexity draw?
So I didn't understand the last part of the question. So I understand that
Yeah, that one. Yeah.
this one. So the simplification of the Rouquier complexes. Yeah. Okay. Yes. So I was a little bit quick, maybe. So this is the naive version. So you just have the cube, right?
Yeah.
And then, like, the idea is that so I can make you a little example with the blackboard. Okay, so can you see the blackboard, the whiteboard?
Yeah.
Okay, so for example, let's take fs squared. So fs squared, so the cube version is bs goes to bs plus bs goes to the unit, right?
Yeah.
If you take bs arrow the unit and you take the product with itself once, you get this. But then you use, like, the fundamental ingredient is some decomposition property of the both Samuelson bimodules, so these products of BS's, and this is the only ingredient actually. So BS times BS, one can show, it's like not so difficult. One can show that this is equal to BS shifted by 1 plus BS shifted by -1. And so, like, I forgot some shifts in my, this is a 2. And then if you plug in this decomposition, you get BS shifted by 1 plus BS shifted by -1. And so what you notice is that here and here you have the same object, for example. And if you compute the component of these morphisms along the yellow, I mean, from this yellow summand to the other yellow summand. This is just the identity. And then you can use what is called Gaussian elimination for complexes and get rid of them. I mean, there is a technique in general, if you have complexes of the form of this form, where the morphism from E to E prime is an isomorphism, then you can get rid of that and just obtain A to B to C to D with a modified morphism from B to C. But you can get rid of two isomorphic elements. And you can repeat, like, this is just like the basic, like the basic brick. And then what I show you, like for the, like those subcomplexes were just like a way to perform this operation many times in a nice way. Like you can construct these CW complexes and see that like a collapse of a face of the CW complex with some of its faces just corresponds to one application of this operation. And then you can repeat and repeat and repeat, and you can get rid of many summands.
Yeah. Okay, any other questions? Okay, let's thank the speaker again then.
Thank you.
Okay. Okay, I'll see you.
See you.
Yeah, bye.
Bye. Thank you very much.
Thank you. Bye-bye.